So far we've been talking about this form of second order ODE, so that's a linear homogeneous ODE with constant coefficients. A, B, and C are those constants, whatever they are. And we learned that to solve this you guess y equals e to the rt, so y is a function of time, e to the rt, and you plug it in and you get some equation to solve for r. So there's a couple of things I need to address before we move on. So first one is the case of repeated roots. So the cases that I showed before, we got two solutions for r because you end up with a quadratic equation for r. And it gives you two solutions, and then you add those two solutions together with arbitrary constants, and you get your general solution. But what if your quadratic equation only has one solution? So an example of that would be something like this. So here's an example of an equation which is exactly the type that we're talking about. So now suppose you substitute in y equals e to the rt. As usual, y dot is going to be r e to the rt, and y double dot is going to be r squared e to the rt. And if I substitute that in, I'm going to get r squared e to the rt minus 6r e to the rt plus 9 e to the rt equals 0. And of course all the e to the rt's cancel out. And I end up with this equation, r squared minus 6r plus 9 is equal to 0, which can be written like this, r minus 3 squared is equal to 0. So it only has one solution, r is equal to 3. Okay. So we know we have one solution, which is y1 of t is equal to e to the 3t. But that's weird, right? This is a second order ODE, and so I should have two solutions with two arbitrary constants in front of them to get my general solution. So how do I get the other solution? That's the question. So I will make a claim to you, and I won't prove it here, but it is in the lecture notes. So if you're really interested in seeing the proof, you can go to the lecture notes and see it. But the claim is, if you have this situation where you have two repeated roots, or you have a double root, right? So r minus 3 squared is what we call a double root to that quadratic equation. And you get one solution, which is r equals to 3, so y1 is e to the 3t. My claim is another independent solution. Independent solution is the same one, except you multiply by a t. So y2, so another independent solution is y2 of t is equal to t e to the 3t. Okay, so it's independent of the previous one because it's not multiplied by a constant, it's multiplied by t. And now I have to prove to you that, well, I will demonstrate that this does solve the ODE. And so let me do that kind of quickly. So here I took the derivatives. I'm just checking that this one that I claim to you is a solution. We're going to check that it's a solution. So I took the derivative y dot, y double dot, and now I'm plugging them into the ODE. So this here is y double dot, y2 double dot, minus 6 times y dot, plus 9 times y. Okay, let's check. What is that equal to? Okay, there's an e to the 3t in every term. Maybe I better go up here. There's an e to the 3t in every term, so let me pull that out. Then there's terms proportional to t and terms that are constant. So let me count the constant terms first. I've got a 6, I've got a minus 6 here, right? So I've got 6 minus 6, so that's 0, right? 6 minus 6. And then I've got terms proportional to t. So what have I got? I've got a 9t here, I've got a 6 times a 3t, which is minus 18, and then I've got another 9t here. So I've got 9 plus 9 minus 18, and that's equal to 0. So it does check out that this is a solution. So in the case where you have roots, two identical solutions to the quadratic equation, to this characteristic equation, you have a repeated root. The claim is that first one gives you the regular solution, r is equal to 3 in this case, and then to find an independent solution, you just multiply by t, and then you have another solution. So now I got my two solutions, and I can form the general solution. Okay, so to summarize, we've got talking about this kind of equation. Generally, we guess e to the rt, r is a constant. You plug it in, you get a characteristic equation, which is a quadratic equation for r. And we've talked about two cases here. So case 1 is if I get two solutions to that equation, r1 and r2, then I've got two solutions to the ODE, which I'm calling y1 and y2, with two different exponents. And then my general solution is formed by just adding those two together with arbitrary constants. Case 2 is if I get only one solution, which I'd call it a repeated solution. To the characteristic equation. Then I get two solutions, y1 of t, so let's just call this r. y1 of t is e to the rt, and y2 of t is equal to the same thing multiplied by an extra t, e to the rt. And then my general solution is going to be equal to some constant times e to the rt plus some other constant times t, e to the rt. Or you could just write it like this, factor out an e to the rt, a plus bt. Okay. So those are the two cases we've talked about so far. All right, there's one more thing I want to do before we move on to a different topic, and this last thing will bring us back to physics. So let's go back to the simple harmonic oscillator, the most important equation, or it's the most important system in physics. The mass on a spring. And we'd already talked about this system before when we were introducing second order ODEs. And we started by drawing a free body diagram just to remind you. So there's a spring force here, Kx, pointing in the negative x direction. And so then if I write down the sum of the forces is equal to ma, there's only one force, which is the spring force. It gives me minus x is equal to, Kx is equal to ma. And a is the second derivative of x, so that's x double dot. And then I get this equation, m x double dot plus kx is equal to 0, or x double dot plus k over m, x is equal to 0. And then we normally define this combination is defined to be omega 0 squared. So I end up with this differential equation, x double dot of t plus omega 0 squared x of t is equal to 0. Okay, k is bigger than 0, m is bigger than 0, so of course omega 0 squared is bigger than 0. Omega 0 itself is bigger than 0. Okay, so when we first introduced this equation, we had talked about how to guess a solution in terms of sines and cosines. But what if I had tried to use the same techniques that we've been talking about in this lecture by guessing e to the rt for this kind of system? So let's try that. try a guess. X of t is equal to e to the RT. So this is supposed to work for second order homogeneous linear equations with constant coefficients. This is one of those equations. So let's plug it in. X double dot, we have to take the derivative. I get 2r squareds from the chain rule, e to the RT. So plug it in. And what do I get? R squared e to the RT plus omega 0 squared e to the RT equals 0. And as usual, these cancel. And so I get r squared is equal to minus omega 0 squared. And r is equal to plus or minus the square root of minus omega 0 squared. Okay, but if you haven't seen this before, this looks strange because remember, omega 0 squared is a positive number. And then there's a minus sign sitting here. So I have here the square root of a negative number. So this is the square root of a negative number. And some of you know how this works, but if you haven't seen it before, this is something you have to think very hard about. You're supposed to not be able to take the square root of a negative number, so this is looking strange. So in order to go forward, in order to actually solve this most important equation in physics, in terms of exponentials, I need to think about how to handle square roots of negative numbers. So that's going to take us where we need to go next. We need to talk about imaginary numbers and complex numbers. And so we need to take a little detour into understanding how to deal with the square root of negative numbers, imaginary numbers and complex numbers, and then we'll come back and solve the simple harmonic oscillator, and then we'll be able to add some drag force to the simple harmonic oscillator as well. All right, so that's where we're going, and then we'll start that in the next lecture.